Hello, this is the second of two video lectures on geologic time. This time we're going to be investigating radiometric dating and biostratigraphy. So let's jump in here. Okay, so you'll recognize this diagram on the right. And this time, what I want you to notice, as well as showing the various time chunks, I want you to notice these numbers in here. These are absolute ages in millions of years ago. Now, one thing I want you to also be aware of is it gets complicated, but sometimes you see millions of years written MA and other times MY. That's about technicalities, but just be aware of that difference. At the moment, just think millions of years. That's the important part. So we have information on the absolute age for the boundaries between each of these time chunks. So how do we get them? Now, you'll remember that absolute age is a number in thousands, millions, or maybe even billions of years ago. And we get this number through the process of radiometric dating, which involves isotopes. And so the first thing we want to do if we're trying to get an absolute age from a rock is we want to know whether there are minerals in the rock that contain elements that undergo radioactive decay. Because if there are, then we can get an absolute age. So for our purposes, to get an absolute age, we want an igneous rock because we know that they lock in time at the time that they crystallize. There are a bunch of complications that involve whether or not they've been melted and remelted, but we're going to just treat it as being a simple story for the moment. So, the study of geologic time and absolute age is called geochronology. So I want you to start by just looking at this progression. We've considered this before when we were looking at rocks and minerals. You'll remember if we have a rock, and here's an example of an andesite, that rock contains minerals. Andesite is a volcanic rock, so we know that those crystals formed pretty much instantaneously when that eruption took place. So they are very good for dating when it happened. Each of the minerals in there contains elements, and those elements, the smallest part of each element is an atom. So this is where we need to dive into a little bit of detail. Radiometric dating is based on the radioactive properties of certain elements. And one thing I want you to note here is that radiometric dating is not the same as radiocarbon dating. We'll look at that later or consider it. So, if we're going to investigate how we get these absolute ages, we need to just remind ourselves or learn a little bit about atoms. So, first of all, if we're just thinking of elements, remember that our elements are all on the periodic table. And here's just two elements shown from a small part of the periodic table. Rb stands for rubidium and Sr stands for strontium. Now, some elements, such as a variety of rubidium go through a natural radioactive decay process. And we use this as a way of getting absolute ages of rocks. So, in order to understand what's happening, we need to just review a little bit about atomic structure, because we have to understand what isotopes of elements are. So, first of all, how do we read the information from the periodic table? This little square for rubidium has a couple of numbers in it. The number up at the top is called the atomic number, and the number down below is called the mass number. Now, let's dive into atomic structure, and then these numbers will make a little bit more sense to you. So, first of all, let's consider an atom. So, an atom is made up of a bit in the center that's called the nucleus. This has positively charged protons and then some neutrons, which are neutral. And then around that nucleus, we have our electron cloud. And those electrons are negatively charged. Now, I want you to remember that that number at the top of the square, up above rubidium, that's the atomic number. And that's kind of like each element's social security number. The reason I call it a social security number is that tells us the number of protons. Each element has a specified number of protons. Remember, they are the positively charged parts that are in the nucleus. And all atoms of the same element, so any atom of rubidium will have 37. Its atomic number is 37. Now, the reason it's like a social security number is because atoms are balanced and don't have a charge, the number of protons always equals the number of electrons, the negatively charged parts. And the number of electrons essentially controls how a particular atom of an element behaves. All atoms of an element behave the same way, but we can predict how they're going to behave once we know the number of electrons. So that's just information on the number of protons and the number of electrons. They are the atomic number. Now, the mass number, which is larger than the atomic number, is also called the atomic weight. That is the number of protons plus the number of neutrons. Now, an element such as rubidium will always have the same atomic number, but it turns out that its mass number can change. And that is because the number of neutrons might change. When the number of neutrons changes from what it normally is, these variants are called isotopes of an element. And they have a different mass. That's because neutrons have weight and protons have weight. And so if you have more or less neutrons in your atom, you're going to change the atomic weight. And just as a reminder, the mass of electrons doesn't really count. They don't have enough mass to be considered in this atomic weight. So an isotope of an element has a funky number of neutrons. Now, so something funny happened here. So what? Now, this is where we start thinking about what we call our radioactive decay. Now, this happens in some elements, not others, but some elements will naturally decay radioactively to produce new elements. So hold that. Now, if we think about our rubidium, it actually decays radioactively to produce some strontium. Now, when we talk isotope, if you want to put it like that, we put the mass number as a superscript in front of the symbol for that element. So we call this rubidium 87. That's how we say this. And that's denoting, okay, it's a particular isotope of rubidium that decays to produce a particular isotope of strontium. This is strontium 87. So rubidium decays radioactively to produce strontium. So now, the next important thing to grasp is that the unstable element or isotope that decays is called the parent. So in that case, rubidium 87 would be the parent. And the material that is produced as a result of that decay is called the daughter product. So in this case, if we move over here, rubidium 87 decays to make strontium 87. So rubidium 87 is the parent, and the strontium 87 that it makes is called the daughter product. So we've got our basic so what. This is what radioactive decay is. Now, the next thing you need to wrap your head around is the concept of a half-life. It has nothing to do with working too much. It's all about radioactive decay. So if we know the precise rate at which the parent decays to produce the daughter, we can then use the proportion of the parent to the daughter to determine when the rock formed. Okay, that's the premise of radiometric dating. And let's look at exactly what a half-life is. Don't worry about the graph yet. One half-life is the amount of time it takes half the parent to decay to form the daughter isotope. So what we've got here on the right is a graph, and we've got number of half-lives. So at one half-life, half of the parent will have decayed to produce the daughter isotope. So let's look at the y-axis, and the title here is percentage of radioactive isotope remaining. So this is looking at the parent. So you start with 100% parent, and this line goes down to one half-life. 50% of the parent remains. These little diagrams here are trying to sort of depict it in terms of the number of atoms. So in this case, there'd be, if you start with 100 atoms of the parent, after one half-life, there would be 50 of the parent and 50 of the daughter. After 2 half-lives, what's happened is, okay, you had 50 atoms of the parent left, half of that decays. So after 2 half-lives, you still have 25 atoms of the parent, and now you'd have 75 atoms of the daughter. And if you look over on the y-axis, you can see that that 25% of the parent is indeed true. And it goes on for 3 half-lives and 4 half-lives. So that captures the concept of a half-life. Now, let's just take a look at this. I suggest you pause the video and try to answer these questions. All right, so if a sample has 50% parent and 50% daughter, 1 half-life has passed. If it's got 25% and 75% daughter, then 2 half-lives have passed. If a sample has only 12.5% parent and 87.5% daughter, which is this spot right here, and they've rounded here, we're at 3 half-lives. Now, what about if there's 75% parent and 25% daughter? So here we go right there, 75% parent and 25% daughter would be right on this line. We read across to where this curve is, and that's half a half-life. Okay, so now that we've got that part of working with half-lives done, let's actually put a number on what the half-life of an isotope is. So if the half-life of the isotope is 40 million years, how old is the rock? If 75%, 50%, 25%, or 12.5% of the parent remains. So pause the video and see if you can figure this out. So the half-life of the isotope is 40 million years. Now, we know that if 75% of the parent remains, we go right there, that is half a half-life. 1 half-life is 40 million years, so the answer there is 20 million years. And I think you can work through these other answers. Pause and figure it out if you can't do it straight away. Now, let's do a reality check. There are various decay pairs that typically get used, and we're learning more and more about some of these pairs all the time. So here, in this table down here, it gives the parent isotope, the actual half-life, and the daughter product. And over on the right column, it shows the range of time over which it is a useful pair to use. And we call them pairs because potassium 40 decays to argon 40, etc. So here are the sort of the age range that they can be used for. So what's important is that these elements are only sequestered in certain minerals. So we need to have an igneous rock that has the minerals that contains this starting material. So we can actually go about getting an age two ways. We can either just get a whole rock age, basically crush up the entire rock and get the chemical information we need. Or we have to do something really painstaking, which is crush up the rock, separate out individual minerals, and do the geochemical analyses from individual minerals. Now, one situation where there can be errors is if the rock hasn't been in a closed system, if maybe there's been some metamorphism or some metamorphic fluids have reacted with the rock to reset it or change it. One of the other problems is if we're using potassium 40, it decays to argon, and argon is a gas, and sometimes rocks experience or minerals experience what we call degassing. They lose some argon for a variety of reasons. But the geochemists and geochronologists are really careful about how they apply these different methods. And there are a bunch of tests they do to make sure they're using the correct approach. So I mentioned earlier, never get radiocarbon dating mixed up with radiometric dating. So radiocarbon dating, it relies only indirectly on any radioactive decay of carbon. And that happens in living material when it dies. Radiocarbon dating only goes back as far as 40,000 years, maybe 50,000 years. It is not usable in any materials older than 50,000 years. And there are a few challenges to radiocarbon dating. One of them has been we don't quite understand whether production of carbon-14, that's one of the isotopes of carbon in the atmosphere, has been constant. What does radiocarbon dating get used for? If there is wood in sediment. One thing one has to be very careful about is making sure that if one collects something for radiocarbon dating, you have to immediately wrap it up in foil, because the information contained in that sample can be messed with if it is exposed to atmospheric carbon or sunlight. So we can get information from some bones. It's also used in archaeology to date manuscripts, particularly those that use some kind of organic inks and or vellum or other material that includes carbon. Okay, so now what we're going to do is think about biostratigraphy. In other words, how the sequence of fossils that we see in rocks can help us build our understanding of the age and sequence in a series of rocks. So what we're looking at here, I want to start, just go through what we're looking at. So we've got simple stratigraphic columns for 3 regions. That's what we're going to pay attention to first. Region 1, Region 2, and Region 3. Each unit is lettered, and there's a slightly different sequence in each of the regions. Ignore the unexplored regions for now. So the first task I want you to think about, and you can pause the video, is put these sequences in order. So you've got a S, O, D, there's a C, and there's an M. Based on what you know about relative age, what is the order of the units based on comparing these three sequences? Pause now. And I'm hoping that the result you got is C, O, S, D, and M. And we got there because we know M is on top of D. And here you have M on top of D. Here D is at the top of the sequence. Now, if we look at this one on the right, we know D is above S. If we look at the area in region 2, D is above O, but on the right, S is between D and O. So now we know that the sequence must have S in between D and O if we compare these two. So now we've got M, D, S, and O, and in region 2, O is above C. Region 2 is the only place where C is present. So we've got our sequence. Now we're going to think about the fossils. And in this simple scenario, we've got two fossils. We're going to call them F1 and F2. F1 is actually a type of trilobite, and F2 is a crinoid. And on this diagram, it shows which fossils are found in which units. The little picture is right next to the unit. So you can put a star in the column for F1 or F2 everywhere that you see that fossil is present. So I'll let you do that. Pause now. Okay, so I'm hoping this is what you determined. M and D just have fossil F2. S has fossils F1 and F2, whereas C and O just have fossils F1. So if you were a paleontologist, you might end up observing that, okay, F1 was living through unit S. And then we have the introduction of fossil F2. Now, there are all sorts of reasons why this may be how it appears. It could be that there's some change in sedimentary environment that prevents fossil F1 from being preserved in D and M. But we're just going to assume for the moment that this is the range of each of these fossils, the time range. F1 was present C, O, and S, and F2 was present from S, D, and M. Okay, so our next question involves, okay, how can we use our knowledge of what we see here if we go to these unexplored regions? What can we learn about the age of the sediments in these unexplored regions? So don't worry about how the patterns for the sediments match. All I want you to pay attention to is the fossils. How do unexplored regions 4 and unexplored region 5 compare in age, or what do we know about their age based on the fossil information that we have over on the left-hand side. So pause now. So because in region 4, we just have our trilobite, we know it's comparable in age to C and O. On the other hand, in unexplored region 5, we have both fossils. That means that it is comparable in age to unit S. And this is how they built our original timescale. You remember, they were using observations of the rocks and the fossils they contained. Now, the next thing I want you to think about is in these stratigraphic columns, we've got some information on some igneous intrusions. So think back to relative dating and cross-cutting intrusions. We know that this igneous intrusion is 300 million years old, and it cuts through O and D, but not through M. On the other hand, in region 3, we have an igneous intrusion that is 350 million years old, and it cuts through O and S, but not D. So what I want you to do now is to determine what we know about the absolute age of each of these units based on this radiometric date that we have. So we want to know whether the unit is older than or younger than 300 million years and or 350 million years. So pause now. All right. So here is the interpretation. And I'm not going to step through everything here, but if we consider unit C, we know that C is older than O, and the O is cut by a 350 million year old intrusion. So we know that C is older than 350 million years. And you can use the same logic for O and S. Unit D is really interesting. So let's go to region 3. Here, the 350 million year old intrusion does not intrude D. But over in region 1, the 300 million year old intrusion does. So D is therefore bracketed to have formed sometime between 300 million years ago and 350 million years ago, whereas M, that is, sits on top of D, has to be younger than 300 million years. So this is an example of how we use biostratigraphy, radiometric ages, and all the basic principles of relative age to build a geologic history. So thank you for your patience. And now it's time for you to dive into your Let's Dig Deeper. There's no quiz this week.